Okay, so I thought I'd record some videos doing some of the workshop problems and maybe giving some tips and tricks for anyone who couldn't come to our review sessions. So I'm starting on Alkene Workshop Part 2, and at the top I have written two little reminders for myself. And the first is that the Markovnikov reaction, the hydrogen bonds to the less substituted alkene carbon, and then the halogen or the alcohol bonds to the more substituted carbon. And if it's easier for you to just remember one thing, then you can remember, for me, I remember for Markovnikov that my X or my OH bonds to the more substituted alkene. And then for the anti-Markovnikov, of course, it's the opposite, and the H to the more goes to the more substituted alkene carbon, and then the X or the H to the less substituted alkene carbon. And then I also have this pulled up to use as a reference. I would suggest making flashcards of these that would include like the reagents that you would need to use, and the products if you need to know the mechanisms and any like important notes. That would be handy if you made flashcards for that. Okay, so for the first part, he wants us to predict the major organic product and then draw the mechanism for that reaction. So the first one is I want to look at the reagent, which is HBr. And if we come over here, we see that there's an HX, making all sorts of scribble marks here. There's an HX and X can be Br. And then there's down here in the anti-Markovnikov, there's another HBr that will probably throw you off. So for this HBr, there's something different in the reagents, and that's the peroxide, the ROOR plus heat. So the way I like to remember, is it going to be the Markovnikov or is it going to be the anti-Markovnikov? I like to remember that for the anti-Markovnikov, the ROOR scares this into anti-Markovnikov. It's roar and it scares it. I learned that from Chad's prep and it helped me. Scares it into anti-Markovnikov. Okay, well we don't have roar here. We just have our HBr, which is essentially the HX right here. So this is the one that we're looking at. We're going to do halogenation, hydrohalogenation Markovnikov. We need to know the mechanism. Oops, we need to know the mechanism, and it does come with a carbocation intermediate. So when you see carbocation intermediate, you want to look for rearrangement. So when you see there's a carbocation intermediate, you need to look for rearrangement each time. Okay, so I have stickers because I don't know how to draw. Shapes are hard. So we start out with this alkene, and we have decided that this is a Markovnikov. So we know that in a Markovnikov, the H bonds to the less substituted alkene, and the X or OH bonds to the more substituted. So we could straight away just predict the product of this. And if we are looking at the original, we're only looking at the alkene carbons. That's my more substituted alkene carbon. This is my less substituted alkene carbon. So right away, you could predict that our Br is going to add to the more substituted, and that the H, which is, we don't draw in ever, bonds to the less substituted. So we can predict the product pretty easily by just looking at it, but he wants us to draw the mechanism. So remember that always with your addition reactions, the thing doing the attacking are these lone pair electrons in the pi bond. So they're going to attack the H first. They're just going to pluck him right off, and they're going to add him to the less substituted alkene carbon because it is a Markov-Nikov reaction. All right. And don't forget to draw your arrow of the bond breaking, because I always do. Okay, so we basically pulled out those electrons from the pi bonds, so they're no longer there. We still have our methyl group sticking out, and now we've added this hydrogen to the less substituted alkene carbon. Okay, and in the process of opening up our double bond there, we made a carbocation. So we're going to draw that carbocation here. So here's where we want to ask ourselves, is this carbocation more stable here, or would he be more stable elsewhere? Well, carbocations are more stable at the more substituted carbon. So between this carbon and this carbon, this is the more substituted, so it is on the more stable carbon. So we leave it there. Okay, now we're going to attack with our bromine. And a good way to remember where your bromine is going to attack is it's kind of easy to see. You've got a minus here and you've got a plus here. And so you can see that this bromine is going to attack where that plus is. So we're going to add that bromine to that, to that carbocation. Like this. So we still have our methyl group. Our hydrogen is still here. You don't have to draw it in. But we do need to draw in our lone pairs. And that's your product. Okay, we'll do the next one. So remember when you have H2SO4 and H2O, so both of these together, that you're going to treat H2SO4 as if it were H3O. And we draw it like that so that you can visually see that we're using the H3O as a proton donator. It's the acid. All right, so we want to ask ourselves, is this Markov-Nikov or anti-Markov-Nikov? And if you haven't memorized your reagents yet, that's okay. You can look at your additions reaction summary. And we see that we have a catalytic acid, H2SO4. And down here, he's even written what it breaks down into, which is H3O, H2O. Okay, so, hi, buddy. I'll be down in a little bit. Sorry, my son just came in. So, we know that we're doing a Markov-Nikov reaction, Markov-Nikov addition, which means that our hydrogen is going to bond to the less substituted, and our OH is going to bond to the more substituted. So let's just highlight which of those are which. It kind of helps to just visualize it. So here's our more substituted carbon, and here is our less substituted carbon. Ta-da! So you could already predict the product, right? You could predict that the OH is going to bond here, and the H is going to bond here, and then we won't have an alkene. But we're going to draw the mechanism. So we start with our alkene. And again, we know that it's these electrons in the pi bond right here that are going to attack our H. And we know that the proton donor in this is our catalytic acid, or H3O. So those alkene carbons, electrons attack our H and the bond breaks. And we get this. Still have our methyl group coming off. Now we've added an H to our less substituted alkene carbon. All right, so now we're going to attack. These are in equilibrium with each other. Now we're going to attack with our water. So remember that we've created a carbocation, and it's the same exact molecule as above, so we've already assessed that this carbocation is on the more stable carbon. So now we have H2O. And H2O is so versatile, and here's a trick for you to remember something about water and how it's going to behave in a reaction. If you have water that's made from a catalytic acid and it's in acidic conditions, then your water is the base, and it's going to either be a nucleophile or it will be a base and it will deprotonate. So right now it's going to behave like a nucleophile. And remember that nucleophiles attack electrophiles, which tend to be more positive. So even though our H2O doesn't have a negative on it, it's still going to act like a nucleophile and attack the electrophile. So these electrons are going to attack that carbon that has the positive sign on it. And we are going to get this molecule that has water on it added to it. So there's our methyl group. Here's our water that's been added. Got our lone pair there. We still have our hydrogen here. So now we have a molecule that has a positive charge, and this can be a good indicator to you that you're not done yet. Up here, we added the bromine, there was no charge, everything was all set. For this reaction, we don't want to leave. This is not stable, it doesn't want a positive charge on it, it's high in energy. So you can see that there's a hydrogen that we can pluck off. And remember how I told you that H2O in acidic conditions can act as a base or a nucleophile. So here, it's acting as a nucleophile and attacking the electrophile. Here, it's going to act as a Bronsted base, and it's going to deprotonate that hydrogen for us. So we can get rid of that positive charge on the oxygen. Oop. And then we get our final product. So we still have our methyl group. Here's our OH bonded to our more substituted alkene carbon. And then we have a hydrogen down here that, again, you don't have to draw. And that's our final product. All right, so the last one that we'll do for this video is in similar conditions. So up above, we have our acid, our catalytic acid and water. Well, down here we have catalytic acid and an alcohol. So if you want to draw that out, it's just a methyl with an OH. And another way you can see it is ROH. So it's going to behave similar to how the water behaved, and it's also going to allow us to add on a methyl group and create an ester with our reaction. So this is, again, going to be a Markovnikov reaction. So we are adding a group to our more substituted alkene carbon, and we're adding a hydrogen to our less substituted alkene carbon. All right. So we'll start, remember this is H3O. Let's just rewrite it. And then this is going to be basically an ROH. But you need to keep in mind that this CH3 group is the R. So you want to make sure that that's what you're adding on to your alkene. Don't forget, don't leave that off. So, okay, the first thing that we want to do is to protonate our alkene carbon and create our carbocation. So our pi electrons are going to attack the H, going to break off. And we will get that H is bonded here. We made our carbocation. Okay, and now our alcohol is going to attack. So remember up here, we protonated, just like we did down here. So here we protonated, here we protonated. Then our nucleophile, which was water, attacked. Now our nucleophile that's the alcohol is going to attack. So I'm going to just draw it like this. And it's going to attack where the carbocation is, just some more substituted. And we get a product that looks similar from up above. We're going to have a positive charge to the nucleophile that we just added. So it's going to, let's draw it. Let's see, this will be our methyl group that was there already, just kind of moved up, and we're going to add then the alcohol here. So we have the O, the H, oops, and actually we'll draw our CH3 down here. So hopefully you can kind of see that alcohol, like here's the H, here's the H, here's the O, here's the O, and then here's our CH3 group. So that's what we've added. It's a positive charge. And if you're ever unsure, just do your formal charge. So we know that oxygen has 6 valence electrons, and we've got 1, 2, 3 bonds plus a lone pair, which equals 5. So it's a positive charge, not 5. So we know it has a positive charge. Okay, so we don't want a positive charge. And remember what we did up here. We took what was originally our nucleophile and it became a base. So here, same thing, our nucleophile is going to become our base and it's going to deprotonate. So we have our OH, our methyl group, and it's going to deprotonate. So we don't have that positive charge anymore. Boop, boop. And we get this guy. That's kind of confusing, sorry. Oops. So here's our methyl group. Here's our OH group. And remember we had the hydrogen that we added down here. With our methyl. So maybe it's easier to visualize this as being an ester if we draw it a little more cleaned up. So I'm going to clean it up a little bit. Here's our methyl group. Here is our ether. Oh, I was calling an ester before, it's an ether. All right, in the next video we'll tackle these. There's some carbocation intermediates that have to be rearranged.